Okay, so today we're moving on to lesson 8.3, and we're going to look at vector and parametric equations of a plane. So first of all, what do we need to actually describe a plane? I have a bunch of planes here before. You can just think of, say, a piece of paper as a certain plane, right? And, well, for example, if I were to take a piece of paper and a pencil, let's say the pencil represents a line, I can put that on the plane, but notice that the plane can still rotate into many different positions and the pencil is still on it. So a single line is not enough to specifically describe a plane. We need something else as well. You can have a point, right? So that'll work. Right? So if I place this pencil here and I place another point there, well then I can't rotate the plane anymore. If I did, either the line or the point would no longer be on it. So I could have a line and a point. That'll work. I could have 3 points because you can create a line between any 2 points. And so now you have a line and a point. I could have 2 lines. Those will work if those 2 lines are intersecting. Or I can have 2 parallel lines as long as they're not coincident lines, meaning as long as they don't lie on top of each other, because that doesn't give me any additional information at all. So these are the things I'm going to need to create some sort of equation to properly define a plane. Okay, now we went over how to define a line, our vector equations for a line. And so what we had was we had some vector r0, which would point to a point on a line. And then we had some other unknown point where the vector r would point to. And then this vector here would simply be just a scalar multiple of our direction vector. But that's just a line. That doesn't describe a plane. So what I could do is I could have 2 lines that go from P0, from our known point, like this, 2 intersecting lines that intersect at P0. And if we simply add those lines or add a combination of a scalar multiple of those lines, we'll get our parallelogram that goes to point P. So what we're going to do is we're going to say this line P0P is just, so P0P is just some scalar multiple of A plus some scalar multiple of B. And then this vector R can point to any position on the entire plane if we simply have the vector R0 pointing to a known point on the plane where these 2 lines intersect, and having these 2 then added to it as a scalar multiple of both. Notice now in this case, when we had a line, we sort of just would cover this up, right? And that was the equation for a line. And you can change S any way you want to get any point on the line. For a plane, we have 2 scalars, both of which can be any real number. And I can change one or the other or both of them to get any point on the entire plane. Now similarly, once I have this is our vector equation for a plane. Once I have that, I can create our parametric equations. So r is just the vector to an unknown point on the plane, x, y, z. Okay, and we only do this in 3 dimensions. And A would be some A1, A2, A0 are not a known point, and B, B1, B2, B3. So we can create our parametric equations. X equals X0 plus SA1 plus TB1 right there. There's our first parametric equation. And similarly, we can create our parametric equations for y and z as well. Okay, so example problems. First example, number one. Determine a vector equation and corresponding parametric equations for the plane that contains, so in this case they're giving us 3 points. Right, now I said one, you can have 1 point and then you can create a line from the other two. Right? Or you can create 2 lines, even better. So let's start off by making a line AB. So we can figure out AB by finding the difference in their coordinates. That was a terrible equal sign. Finding the difference in their coordinates. So we have -1 minus -1, so that just gives us 0. 1 minus 3, so -2. And 0 minus 8, so -8. So there's a vector. But notice that we can write that as just a scalar multiple. It's almost like taking a fraction and putting it in lowest form. We can write it like this. Right? So let's call A, which will be one of the lines we'll use to define the plane, as 0, 1, 4. Which is perfectly fine to do because it is a scalar multiple of AB and therefore parallel to AB. All right, let's use another line because we want to figure out what B is. So BC, let's figure out what BC is. We'll find the difference in those coordinates. So 4 subtract -1, that's 5. 1 subtract 1, that's 0. And 1 subtract 0, that's 1. And that looks like it's in lowest form there. So I'm going to just label that as being our vector B. Now I can write our vector equation for the plane R equals, we need some known point on the line. We have 3 of them, so we have our pick. It doesn't matter which one you use, right? Just like the vector equation of a line, there's an infinite number of equations that will describe the same plane. So I'll just go with A, it's the first one. So -1, 3, and 8, plus some scalar multiple S of A, so 0, 1, and 4, plus some scalar multiple T of B, 5, 0, 1, where S and T can be any real number. Okay, and that is our vector equation of the plane. It also says to find the parametric equations. So we can do that. So x will equal -1 plus 0s, so that doesn't do anything, plus 5t. So plus 5t. All right, our y equation, we have 3 plus 1s, or just s, plus 0t. We just leave that as s. And lastly, z. We have 8 plus 4s plus t. Right, so there's our vector and parametric equations for that plane. Now part 2, this does look like a very similar question we had when we did lines. Do either of these points, P or Q, lie on the plane? So just like with lines, what we did with lines is we'd see if the values of our scalar multiples, in this case we have 2 of them, S and T, all give us the same thing. So how are we going to do this one? So let's start with P. So here's P, do a different color. P is 14, 1, and 3. So what I'm going to do is in our first equation here, I'm going to substitute 14 for x. So we get 14 equals -1 plus 5t. Okay, then I can solve for t. So add 1 to both sides, and we'll get 5t equals 15, or just t equals 3. All right, now let's take equation 2, and we're going to substitute 1 for y. So we have 1 equals 3 plus s. All right, solving for s, that's not too bad. Subtract 3 from both sides, 1 minus 3, s equals negative 2. Now what I'm going to do is I'm going to look at equation 3. I'm not going to sub in 3. I'm going to solve for z. If I do get z equals 3 when I substitute the values of t and s, then that point is on the plane. Now notice the points P and Q. Q also has the same x and y coordinates, but they have different z coordinates, so only one of them is going to be on the plane. Let's see what we get. So when we get z, this is equation 3, z equals 8 plus 4s, where s is negative 2, plus t, where t is 3. So we do that, we get 8 minus 8, which is 0, and we're left with 3. Ooh, the drama. P is on the plane. Q is not. Okay. Now example 2 says a plane pi. So we usually use the symbol pi to represent a certain plane, just like when we did lines, we gave the line a capital L. Okay, so we have some plane pi with this equation. Determine the point of intersection between that plane and the z-axis. So I want to know where the z-axis actually goes through the plane. What are those? What is that coordinate? All right, well, I'm going to take this vector equation and look at its parametric equations. So let's write those. So x equals 6 plus 1s, or just s, plus 2t. Okay, let's find out what y is. So negative 2 plus 3s plus 2t. And finally, z is minus 3 plus 0s, and then minus t. And the point I'm looking for, since it's going to intersect the z-axis, we know the point is going to have x and y coordinates of 0 and a z coordinate of, I don't know, some value a that we're going to have to solve for. Okay, I'm going to have to do the rest of this work at the side. So let's start with our x parametric equation, and I'll substitute 0. So 0 equals 6 plus s plus 2t. And I can sort of rearrange that a little bit to give s plus 2t equals minus 6. Let's do the same for y. So y is 0 equals minus 2 plus 3s plus 2t. And again, I can sort of bring the negative 2 to the other side and write it as 3s plus 2t equals 2. Now let's say this is equation 1, and that's equation 2. What I'm going to do is take equation 1 and subtract equation 2. So I have two equations for two unknowns. I want to solve the system. Figure out what s and t will have to be. All right. Now this works perfectly because you get 2t minus 2t. So t's are gone, and you end up with negative 2s. So s minus 3s equals, and negative 6 minus 2 is negative 8. So we get s equals 4. And if we sub that back into our first equation, which is s plus 2t, we get 4 plus 2t equals minus 6. Or solving for t, you'd have 2t equals -10 or t equals -5. So I know the values of s and t, which are required for those direction vectors to show us what the point will be where our plane intersects the z-axis. So let's take our third equation, z, and substitute what those values of s and t need to be. So for z, that's going to equal -3. We don't actually have an s term, but if you did, that's where you would use it. And then minus t, which is -5. So -3 plus 5 gives us 2. So our value of a is 2. So our point, therefore, is 0, 0, 2. That is where our plane will intersect the z-axis. So our last question says, determine the vector and parametric equations of the plane containing the point P and this line. Okay, so let's look at that. Here's the line, which we've labeled as L. And here's the point P. Now this line, you'll notice, gives you the point, or a point, that is on the line, 1, 1, 1. So let's just call that A. So we know a point on the line, and we know P. That can give us our second needed direction vector for a plane. So let's figure out what AP actually is. So we find the difference in those coordinates. So 1 minus 1, okay, 0. -5 minus 1, so -6. And 9 minus 1, so 8. Again, you don't have to do this, but it looks like I can easily write this as a scalar multiple by pulling out a -2. So 0, 3, -4. So that 0, 3, -4 is our second direction vector that we need to properly describe our plane. So we can write our plane then as, this is r, so I'll call our plane r pi, is, we have a point, 1, 1, 1, plus some scalar multiple of this line, which this direction vector tells us, -1, 1, and 0, plus some different scalar multiple t of this second direction vector, 0, 3, and -4. Okay, so there's our vector equation that describes the plane. And then we can just write, I'm going to do this down below, we can write our parametric equations for that plane as x equals 1 minus s, so 1 minus s, and then plus 0t. Y equals 1 plus s plus 3t. And finally, z equals 1 plus 0s minus 4t.